So I heard a couple of years ago about this fantastic new programming language called Pony that promises to compile your programs down to bare metal. It implements the actor system and this Erlang stuff, which has infected my brain so much. It also uses the actor model. And wouldn't it be great if we could combine the two and have the best of both worlds, and we could have an Erlang Pony? It's not quite so easy, or at least I hope to convince you that it's a worthwhile thing to study Pony on its own, or perhaps do a mashup and then write papers about it for the Erlang workshop coming up this September in St. Louis, Missouri. So anyhow, thanks for the introduction, Jim. I'm at GitHub and Twitter. My handle is SLFritchie. I eat and cook a lot of Japanese food. And I'm currently at Wallaroo Labs, working primarily in Pony, been out of the Erlang world for a little while. So having to write this talk has been a good reintroduction to some very Erlang-y things. I wanted to spend one slide on Wallaroo, which is my company's product, not because this is a product pitch, but to try to try having it in the back of your mind for deciding why you might want to not necessarily use Erlang for an application like this. So Wallaroo is a data streaming processor for easy scaling of data stream applications that are written in Python or Go, more languages to appear later, and to target use cases that aren't so well served today by other open source products like Storm or Spark or Flink, in terms of targeting very low latency for efficiency reasons, having very predictable low tail latencies. The Wallaroo Labs founders come from fintech backgrounds, and high-speed financial traders have different ideas about low latency and high speed than a lot of other people. Also very easy FFI to these foreign language interpreters like the Go runtime and the Python runtime. Wallaroo Labs is hiring. Contact me if you'd like to know more. There are some stickers downstairs on the coffee tables if you need stickers to decorate your machines or your refrigerator or something. Wallaroo actually would be a pretty good Erlang app. There's actually something in the open source world today called Cloud-I or Cloud-E, I'm not quite certain how to pronounce it, that covers several of the bases that this distributed system that Wallaroo Labs has written in Pony. But we, the company, chose to use Pony, and hopefully by the time you leave, you'll have some understanding why. So the outline of this talk, I feel a lot of people, a lot of Erlang users, Elixir, et cetera, feel that the Beam implements the actor model. And I'm here to convince you that that's true and not true at the same time. So we'll just call it false. I don't have nearly enough time to give the sort of background on the actor model that I had hoped, so I'm going to distill it down to one very biased slide. We'll talk about the definition of the actor model. The fat middle of the talk will be 20 or more dimensions about how you might design and or implement the actor model from a practitioner's point of view. Compare and contrast how Beam deals with actor-related things compared to Pony, and then sort of stuff that falls in the basket outside of actor-related stuff but makes Pony really cool, something you might want to think about for new projects. So I hope you have a better understanding where the actor model came from, and that the Beam is really a quite opinionated implementation, but there are others. Pony and Erlang share a really lot of similarities. We actually quantify this in the talk, but there are some few exceptions that turn out to be pretty big, kind of a big deal. And if you have ideas on how to make that much less of a deal, there's some publishing opportunities for you coming up in the future. And then I really hope that you have some interest in learning more about Pony in the future, and that type systems are really amazing tools, and for even if you never touch or look at Pony again, don't ignore the dialyzer. Use it as part of your workflow, and I'll return to that topic in a little bit. So the history of programming in one terrible slide. So, in the 1940s, programming is really cool, and it helps the UK shorten World War II by by months or even years. And then we discover almost immediately, well, writing these things and debugging them is not easy. And then industry introduces time sharing and concurrency, and that makes life even less easy. And programming languages are invented to help deal with the complexity, and structured programming is invented to deal with the complexity. But managing this concurrency is now difficult. And then when we have multiple CPUs in our systems, whether they're tiny little microcontroller things or if they're full-blown general purpose cores, things suddenly become wicked hard in terms of implementation. So Joe said it quite well in his talk, that we have to fight complexity or we're going to go insane. So I hope we take that as gospel. I didn't have enough time to talk more about the background. So here's the point where I try to convince you that the beam is not exactly equal to the actor model. So here's the definition. Some people might boil this down to 3 points instead of 5 or 6. But the actor is the fundamental unit of computation, of computing stuff. Each actor has its own private state, its registers, memory, whatever. And that this private state is readable and modifiable by its owner, but it's private. No one else can read it. That's why they call it private. An actor can send a message to another actor. The actor can react to a message that was sent to it, sort of implying that message passing is the only way to communicate between actors. And actors can create a new actor. So the system can be dynamic. It doesn't have to be fixed in terms of static number of total actors. In the 1980s, there was a lot of work, various projects to try to manage, to reason about and mathematically model the complexity around concurrency. From what I can tell, Tony Hoare in CSP had some publications first before things that came a couple years later, process calculus, pi calculus, and stuff like that. Academics in the room can yell at me now or later about the ordering of that. But the publication of this book on the right, Tony Hoare's book in 1985, came out at a really fantastic time to then influence, among others, the folks in the CS lab at the time who were trying to work out what was a good way of writing controlled software for telecom systems. And so if you take the Communicating Sequential Processes book and this opinionated telecom giant who feels that it knows what networking, telephony and data networking equipment should do now and what it ought to be doing in the future, and combine it with some ambitious researchers, you end up with Erlang, which then leads to the beam. So to get a little bit more specific about what an actor system typo ought to be really ought to implement, I'm going to go really quickly over this and then dive into more detail. So in terms of message sending, some choices to make are whether message passing is synchronous or asynchronous. Do processes have names? What's the destination of a message? Is it a process or is it a channel or some other thing? Is the pattern of messaging one-to-one, or is it a broadcast one to everybody or one to some fraction? Do you need to know who that fraction is? Do you care? Do you have to set that up ahead of time? Is it static or dynamic? Are the messages typed or untyped? When you receive messages, reliable or unreliable delivery, are there blocking semantics? Are you aware of time as things in the model and in the implementation? How are actors scheduled to execute? When you start running them? When do you stop running them? Is the scheduling preemptive or not? Memory limits. What do you do for in-transit messages or at-rest messages sitting in a mailbox or channel or whatever the hell you want to call it? Are there limits on the actor size in terms of heap or something like that? If there's a penalty, is there a penalty for violating any of those limits? Message delivery order, is there any kind of order at all? Any sort of guarantee? A lot of papers that if you read will state up front whether message duplication is allowed or message loss is allowed as part of the model. Actor lifetime, do actors exist forever? Can they crash? How do you interact with the parts of the larger system that are not actors? And then can you tolerate Byzantine or malicious actors as part of the model? So that's a lot. I'll go slower here in a little bit. But if I tally all this up, we get over 20 of them. So for message sending, is it synchronous, asynchronous? And in both the Beam case and the Pony runtime case, they are asynchronous. So yep, we're the same. We like that decision as an overall community. So we're all in unanimous agreement. Processes have names in both cases. In the Beam world, they're named either by PID or by Atom in a process registry. Pony, they're named by a tag address, and you have to have that. You need to have that tag in order to send a message to an actor. There is no process registry equivalent. Message destination. In both cases, it's to the actor. Beam, it's a process, but Pony calls them actors instead of processes. When we're sending messages, are they typed or untyped? Beam, they're obviously, well, I don't know if it's obvious, but they're untyped in the sense that you can send any term to any other process. In Pony, these messages are type checked at compile time. And here's our first major difference. Whoa! That's a Pony joke. The jokes only get better from here on out. Reliable versus unreliable delivery. Here you have to do a lot of hedging, especially in the Beam case. So we'll talk only about single process, single virtual machine, because the semantics for distributed Erlang are different in terms of reliable message delivery. So in the Beam, it's reliable-ish. It's reliable inside of a single virtual machine. And then there's the other caveat that if you send to a process that's dead, the message won't get delivered. If you send to a message with a registered name and that name hasn't been registered correctly, either because the process died or because you invented a name that hasn't been registered yet, then you will crash, and you might then cause a cascading crash of other processes. So we'll call this similar because in Pony, the message delivery is reliable. And we'll get to the whole crash thing a little bit later. Message delivery, Beam, you can use selective receive and pattern matching, and you can change the order of how you actually receive and process the messages. Pony, it's first in, first out only. You have no other choice in the matter. So that's another big whoa. Message ordering guarantees. Again, is there causal message order? Again, we have to insert a lot of caveats. So dealing with a single VM, and also assuming that you're not using selective receive, and you just use the anything pattern to receive a message, then the message order is causal. And in Pony, it's always causal. And that ends up being very important for properties of the runtime and garbage collection later on. Message receiving, blocking or non-blocking receive. Beam, yes, you can block using selective receive and a combination of selective receive and or the after clause and its timeout. You can get some messaging in actor systems would allow you to receive only messages from a particular actor or messages of a particular type, and you can fake that with selective receive. Pony, no, not so much. That's another whoa. Awareness of time. Beam is aware of time using the after clause in your receive statements. And timers are sent as events, as messages, but they are separate things, and they're not combined in the same receive clause after clause sort of way that we're used to dealing in Elixir and Erlang. What is scheduling the actors? We're back to rough agreement here. Both systems have custom schedulers, typically running one scheduler per CPU core. What each of them does is pretty specific to either the Beam or to Pony. You can configure the system to have more schedulers or fewer schedulers per CPU core, but one per core tends to work out pretty well. Both of them are running in pthreads that are scheduled by the operating system, and that's what schedules the schedulers. The beam overhead, sorry, I was lazy and I didn't look up how many small hundreds of bytes there is per process. But it just takes a few microseconds on typical hardware today to create and destroy them, so we call them cheap. And scheduling millions of them alive at a time is not a problem with the beam and its schedulers. Pony, that number's probably incorrect. It's probably more like 256 or 260 bytes per actor, but it's the same very small amount of time to create and destroy actors. And so we'll call that the same. Preemptive versus cooperative scheduling. Here's a really big difference. In the beam, the scheduling is preemptive. And in terms of the Pony, it's cooperative scheduling. And maybe at the Q&A, well, I don't have any code to demonstrate necessarily, so it would be hand-waving talking about the Q&A, but if you have questions about how the cooperative scheduling works, I'm happy to do that. Are there priority schemes that the scheduler takes into account when deciding what to run and for how long? Beam has four levels, 5 levels. How many is it? Four-ish? Four-ish, okay, good. And then Pony doesn't have any. Do the schedulers do work stealing? So if you have multiple schedulers and there's a lot of actor or process things waiting in one queue and other scheduler queues are empty, is there a way to somehow move those processes from the long queue to the short queue and lower the latency for resuming calculations for that process or actor? The answer is both, or for both is yes. I'm not 100% sure if the work stealing for the beam is aware of NUMA zones inside of the machine. Maybe people could qualify that during the Q&A or something. My understanding, without actually looking at each line of code in the scheduler for Pony, is that the Pony work stealing is NUMA zone aware, so it will try to keep processes moving to different cores on the same NUMA zone if possible. Energy conservation by idle schedulers, both do so. Trying to do the work stealing too often can cause contention in system buses and memory and stuff like that. And so it would be great if they would somehow put themselves to sleep and you get some energy conservation as a part of that. Both systems do that. Yay, that's great. Mailbox limits, not so much. I haven't been in the Erlang community long enough to know, like, if in release 20, if there's a mailbox size limit. I heard over dinner a night or two ago that there is a hidden process flag or attribute to set the limit. So I may be wrong here, actually, but in terms of the Pony runtime, no, there is no mailbox limit, which comes with all the pros and cons of that design decision. And if that limit does exist in the beam, my apologies for not looking that up, the default decision is no limit, with all of the wonderful benefits and horrors that can cause during high workloads. Is there a maximum heap size for the actors, the processes? No, given possibly recently out-of-date info in my brain. My apologies, but we'll call it the same because of the defaults. Actor scheduling, so we already talked about the expense of the actor lifecycle. Can actors crash? Processes can crash in the beam. We know that all the time. We have some very lovely mechanisms for dealing with their failure. And if folks are interested in outlining that some more, the Q&A time, please. But in Pony, actors don't crash. The type system provides a lot of safety guarantees, and then the compiler is also requiring explicit error handling of errors in the code. There's actually syntax that you have to use to explicitly annotate that you're calling a function that may throw an error, and you are required to catch it, so there's no such thing as an uncaught exception. So actors are not crashing so much, and that has some implications that are different than in the beam. Do we have back pressure to reduce overloaded actors? The sender penalty in the beam has been there in prior releases, and within the last few weeks, I guess, the process of removing this has been done, and Remo had talked about that earlier today. So the answer is kind of switching here. The sender penalty involved having a scheduling penalty to attempt to slow down a process A sending messages to process B, where process B had large mailboxes. It complicated the code. It didn't work so well in all cases. It has some nasty side effects. And so I can sort of understand there are really good reasons why the OTP team is ripping that out. Pony does have a back pressure system, and I can talk in more detail about that if folks are interested. In the interest of time, I'll skip that for now and can return. Covered a little bit of these things about causal message order. Theoreticians are quite interested in these four properties in particular. You see them stated in a lot of models pretty upfront in the big bold type at the beginning of the papers or the beginning of the models. So message loss, no. Same properties. Message duplication, no, not allowed. Message reordering, we already talked about, is a big deal. Interacting with non-actors, I'm going to call these similar. In both cases, the way that we deal with this is that we convert these events, things that happen in the non-actor-oriented part of the world, and we convert them to messages, and then we start sending them to actors, to processes. The beam is more advanced here in terms of the port. The port data type is the facade that Erlang code uses to think that it's sending messages to another Erlang process. The thing behind that port is frequently an operating system thing like a file descriptor or a network socket or an external process communicating by pipes or something like that. The beam also was using the port for file I/O, and that's being switched over to using BIFs or NIFs and the dirty schedulers. The Pony does not have that same extent of taking things outside of the very specific actors and converting their events into messages. The two things that are network I/O with network sockets and timer management. And timers are delivered as messages again to the actors. Byzantine actors, I'm going to call these the same. One could try to make a case that in the beam with processes crashing, or my favorite thing to do for testing Erlang system robustness is to fire up the appmon. You get this little GUI with representing processes in supervisor hierarchies, and you start playing chaos monkey by saying kill that process, and then watch what happens, right? So in some models that would be malicious behavior, but in terms of my understanding of how most academics and folks who are building mathematical models, is that really a malicious actor? And I would think that they would say no. So I'm going to call this the same. So in review then, similarities by category, 13 same and 5 similar. So we definitely have a majority here compared to the 8 big differences. And for the summary then of the big differences, I've put the big 4 on top. Selective receive and message reordering by the beam being able to block for specific messages, and therefore reordering message reception, being aware of time and being preemptive scheduling. These are big differences. There's no simple, easy, one-to-one translation of we can take Pony code and its assumptions of how actors work, and just very naively translate that into Erlang and have the program behave in the same way, and going the other way is not super straightforward. If you know of techniques that we should be using to try to do that sort of thing, then there's this thing called the Erlang Workshop that's taking place at the International Conference of Functional Programming, and that will be taking place in St. Louis, Missouri, coming up this September. The call for papers should be out soon, I believe. So paper proposals, abstracts, drafts, et cetera, would be in the May timeframe. So we'd like to hear from you. But these other differences are significant, right? Sort of by definition, I call them woe, right? So to just think for a second, again, sort of making this very naive transition, taking some Erlang code and put it in a Pony runtime. In Pony, you can't just call a gen server. The gen server the call doesn't work this way, and because you can't block waiting for the reply. You just can't do that. Runtime won't allow you to do that. And then the message that comes back, the reply to your gen server call, has a reference embedded in it, and so there's also selective receive pattern matching happening there, and you can't do that either. So you would have to structure all of your code to, among other things, cast style or naked use of the exclamation point to send messages asynchronously. So if you think about the amount of Erlang code or Elixir code that you would have to change in order to deal with this restriction, I mean that's a pretty big change. So that was sort of the compare and contrast section. I hope I'm not talking 9,000 words per minute. If I am, raise your hand and tell me to slow down. I have a bunch of stuff that falls not really directly in the basket that you would call actor model stuff. 10 minutes. And so I'm going to go over some of these briefly and some in some detail, and then Q&A. If you have questions about some of them, I can backtrack. The language in the runtime safety guarantees, the compiler and the runtime, of course, fitting hand in glove to provide these properties. It's type safe, memory safe, exception safe, data race free, and deadlock free. That's a lot of goodness packed into one slide. I mean, this is pretty amazing stuff. So one of the effects of being data race free is that all of the message sending in the Pony runtime is passed by reference, or passing pointers around. We're not doing the thing that the Beam does, which is to copy data from the sender's heap to the receiver's heap. All of this sharing is guaranteed between the actors is guaranteed to be safe, data race free. Sylvan Klebsch, who's one of the main designers of the language and wrote his PhD thesis about it, as this lovely quote: "If it compiles, it's data race free." That's fantastic. You, as an application developer, you don't need locks. There are no deadlocks. There's no memory model ambiguity, no concurrency composition problems, and no runtime overhead for these safety guarantees. It's done at compile time. I'm not so familiar with Rust. It's with the possible exception of the awareness of concurrency. These guarantees are similar or the same, quite similar or the same as Rust's. Feel free to fill us all in a Q&A if I got that wrong. But the type system was co-designed to be fully aware of actors and concurrency. And that's how the compiler can figure these things out. Because it's actually aware of concurrency. The compiler is fussy. The compiler is really fussy. But it's saving you from doing bad things with sharing data across actors. And so it's always right. There isn't, coming from the Erlang community, I sort of wish that it had a give me a break mode, or something saying, just ignore that particular one. There are bugs in the compiler, and Pony is a young language. But that means that the compiler is like 99.99% right, which means you're still almost always wrong. And there's some data safety thing in there. And so as a pitch for the dialyzer, I mean, these type systems are amazingly powerful tools. And the dialyzer is finding bugs in your Erlang code and bringing it as a fully supported and usable experience in the Elixir world is fantastic work. Everyone should be using it for finding and fixing their own bugs. If you commit sins like I do occasionally as a long-time Erlang developer, starting before the dialyzer existed, overlooking it is easy to do. It's easy to be lazy, so you should be putting dialyzer in your workflow so you can't ignore it, because these type systems are doing good things, keeping bugs out of our systems. I'll stop preaching now for a little bit. I will have some brainwashing coming up about micro-benchmarking, though, so that's coming up. Pony compiles down to the target CPU, unlike the Beam. There is an optional compilation using Hype to compile Beam code down to native code. Pony is not interpreted by a virtual machine, compiles down to the target CPU. The two different CPUs are supported. JIT is just-in-time compilation is available also through the LLVM toolchain. Dwarf symbols are embedded in your executable, so it looks like C++ with weird name mangling if you're using a debugger or a profiler, but those tools do work. Actors don't crash. This is a side effect of safety. So I mentioned that question mark, that you have to mark a call to a function that may raise an error. And this is enforced by the compiler, again, as part of the compiler's fussiness. And it does mean that actors don't crash. So this whole notion of, do we need links and monitors to help manage failure? Well, if failure doesn't happen, do we need links and monitors? It raises an interesting philosophical question. The reason that the message order can't be tampered with, and why causal delivery order guarantee is important, is because of distributed garbage collection. So garbage collection is distributed across all actors' heaps. This is a thing where both systems agree that per actor, per process heaps is a good thing. So both systems are in agreement here. There is no stop the world GC in Pony. It's fully concurrent, sync-free, lock-free, barrier-free in the implementation. Message passing behind the hood maintains reference counts on shared objects, and as shared objects go out of scope on a foreign actor, the compiler has inserted stuff that will send messages back to the owner heap to adjust the reference counts accordingly, so that when all of the foreign aliases are gone in other actors, that then in the next garbage collection cycle for the original sending actor, that object can be reaped. The concurrency, the type system, and garbage collection are all co-designed, designed at the same time. The protocol is called Orca, as in killer whale, except it's an acronym, not an actual killer whale. I mean, like you want a killer whale in your machine. But actors are first class, and they're garbage collected. So if there are no other references, no other tags to other actors, and the tag isn't waiting for some event from a timer or socket I/O, then the runtime notices that and will garbage collect the entire actor. Once all the actors have been garbage collected because they no longer have work to do, then the whole system shuts down, and that's when your that's when your program, your operating system process stops. On paper, the Orca protocol works for distributed garbage collection across multiple machines. So it is vaporware yet. It's not as vaporware as Xanadu. If you're interested in working on this kind of distributed garbage collection, there's some really great academic work showing the viability of the Orca protocol. It's time for brainwashing. So benchmark propaganda. This is all believable. This is all true all the time, as I'm telling you now. So this is taken from a paper by Sylvan and others at Imperial College a few years ago, looking at the latency in micro-benchmarks of the garbage collection. And so we have 4 garbage collectors. Orca Erlang, the C4 pauseless GC in the JVM, and the G1 garbage collector in the JVM. Lower is better. The y-axis going up is latency. And so the Orca line is much lower than those other ones, so that's better. Yay. Same paper showing the scalability as we increase the number of cores, the number of schedulers in the system. Again, lower is better. For these micro benchmarks, only 3 garbage collectors this time. We have Orca, Erlang, and the Azul pauseless C4. Orca's bars are so tiny compared to those other ones. So of course that's very good too, right? It's believable all the time. And then here's some more graphs. And so you must believe now, I have demonstrated that the Pony's GC is pretty amazing, at least for some definitions of amazing. It's at least very different from how garbage collection is handled inside of the Beam. Pony's not a functional language. It's very imperative. Mutating state it's weird. It gives me the heebie-jeebies even now as an Erlang developer. But the type system makes it safe to do so. So that's quite nice. Pony has lambdas and more. You can do lots of functional stuff. There are persistent data structures of many kinds in the standard library. Pony's object-oriented, but it's not Java style. Not everything is an object. You can control what is a subclass of what. There are 2 types of subtyping. You can declare an interface in a Java-like manner, the Java interface for structural typing. We have generic types. We talk about those if anyone's really interested, but they bend your brain, or at least they bend my brain, because I'm not used to that, because Erlang doesn't really do that, because it doesn't need it in the same way. There is pattern matching available. There's a match statement to do basic pattern matching on data types and super and subtypes and tuple element destructuring. Function head matching is gone, but that's because the implementation, the compiler was buggy. So rather than continuing to confuse people, that it's been ripped out and hopefully will come back soon. It's open source. It's available at GitHub, compiling to 2 different CPUs, 3 well-tested operating system support, Linux, Windows, and OS X. The BSDs have some limited support. I haven't actually personally used the ARM target CPU, but others have. It is supposed to be working. Pony's young. The community, the library is small. The community is small. Third-party available source is a little small. We're looking for contributors from interested people. The FFI to C and C++ code is quite nice. There are a number of Pony primitive data types that map very directly onto the target CPU primitives as well, in terms of integers and arrays of U8s to represent contiguous unstructured bytes. The reference capabilities, this is the static type checker. That's the price to pay as learning how to use Pony. That's the price to pay for all these safety things that I've talked about. And it's a big mind shift for an Erlang or Elixir user. Like I mentioned, mutable data is a little, it's just weird. But again, the type system will tell you when you screw up and you do something that is unsafe. The advantages are really quite great in that there's 0 runtime cost for that safety, and the garbage collector is quite quick. If you'd like to get involved, you can find at ponylang.org the runtime and other tools are available at GitHub under the Ponylang organization. There is an official account at Twitter. Also, IRC support is available. There's a mailing list. If you have questions about Erlang or Pony or Wallaroo for the time remaining here at the conference, feel free to ask. Also available at Twitter and by email. So at that, I'm at 40 minutes or so. So close enough. Thank you for your time.
Is that supported?
That is not supported.
Oh, so everything.
So that omission in my presentation was very intentional, and I probably should have put it. Sorry. What's not supported, right? So the question was, I seem to have omitted message passing in Pony runtimes across different runtimes, and the answer is you can't do that directly. There's ongoing academic work to do that, but that's part also. My understanding is those efforts are tied to implementation of the distributed Orca GC protocol, and so that is not available today.
So how garbage collection actually works with the cooperative multitasking? Is it like you need to yield full garbage collection for?
Right. So the Pony syntax for receiving a message looks like a method definition on an object, and in Erlang terms, that object method definition would get converted to a send part, a send half, and the receive half. When the method has finished doing the processing, then that's when garbage collection may happen, and that's when the cooperative scheduling may also happen.
How does not blocking message queue work?
So you have
Not blocking receive.
Yeah. There is no equivalent to the Beam's receive clause. You can't just arbitrarily insert a receive somewhere in any function anywhere. That whatever behavior function that an actor is executing has to finish, and then the runtime says, oh, there's another message in my mailbox, and according to that type, I need to execute this other method, and then decides whether or not to schedule it now or later. So those mechanics are just kind of hidden from you and done by the compiler and the runtime. I hope I answered your question. Is it close?
Yeah.
Okay.
If everything is passed by reference, doesn't that amount to shared state?
It is, but once you pass it, sort of like if anyone in the room is familiar with Rust, there's the notion of the borrow checker, and you can pass ownership of mutable data to another actor, but that means you give up the ability of that function, at least in Rust, to be able to modify the data unless it gets the ownership back. So in Pony, there are two ways that you can share data. One is that the reference capability on the data that you're sending means that it's immutable. It's basically read-only. Unlike Rust, you can actually pass a capability for something that says it's basically the same semantics as a Beam reference, that you can basically test it for equality, and that's about it. So you can reduce it down to that. You can only test for equality, which is useful in the same way that Erlang references are used for testing for equality or not. You can use that tag. That's enough information to send a message to an actor. That's the minimum handle on an actor that you need to send a message to it. Or you make the object is readable, but no one else, not even the sender, has a writable alias to it, so it's effectively immutable. Or you and the syntax that you have to add in order to do this is you destroy your writable alias to it when you pass it as an argument in the message. In which case, then the receiving actor can get that capability and then write to it. But the sender is hands off at that point. It can't use it.